Hi students, in this video we are going to look at some important function associated with a probability distribution called moment generating function. We are simply going to call MGF. It's actually going to give a complete information about the probability distribution when it exists. So it can serve as the alternative specification of the probability distribution just like the CDF, PDF or PMF. Okay. First let us look at the definition. MGF of the random variable x is denoted by m sub x, which is a function defined to be expectation of e power tx provided this expectation exists for all t in some neighborhood of 0. That is, for some h positive, this expectation of e power tx should exist for all t in the interval minus h to h. Then we say MGF of x exists and which is a function defined on the interval minus h to h. Okay, fine. Now let us look at some examples of the probability distributions and see if MGF exists. Okay, fine. Here is an example of a discrete distribution with a support Sx equal to 1, 2, 3 so on and PMF Px of n equal to 1 by 3 times 2 by 3 to the power of n minus 1 for n equal to 1, 2, 3 so on. Let us see if MGF of x exists for this particular distribution. For that we need to see if expectation of e power tx exists for all t in some neighborhood of 0. That is, for some h positive, we want to see if expectation of e power tx exists for all t belongs to minus h to h. Okay. To see this expectation of e power tx exists, we need to consider this summation n belongs to Sx mod e power tn px of n. If this summation converges for all t in some neighborhood of 0, then MGF exists, otherwise not. Okay, let's see. Here exponential function is always positive, so we don't have to put modulus for this e power tn, and support is 1, 2, 3 so on. So we write summation n equal to 1 to infinity e power tn. I replace this px of n with 1 by 3 times 2 by 3 to the power of n minus 1. Now here this 2 by 3 to the power of n minus 1, let me realize as 2 by 3 to the power of n by 2 by 3. Okay. Now if I take this 1 by 3 and 2 by 3 in the denominator out, it will look like this. Okay. So 1 by 3, this 2 by 3 in the denominator go out, it will become 3 by 2. So this 3 cancel, and the remaining thing, this e power tn, this 2 by 3 to the power of n, you can group like this, 2 by 3 e power t to the power of n. Now this summation look like, if you know the geometric series, which look like a plus ar square, okay, so on ar to the power of n. This is geometric series. This series converges only when mod r less than 1. Okay, here r is the common ratio. In this case, a equal to r equal to both are 2 by 3 e power t. Okay, the first term a and the common ratio both are same, which is 2 by 3 e power t. So this series converges only when mod r less than 1, that is mod 2 by 3 e power t less than 1. Anyway, 2 by 3 e power t positive, so we don't have to put modulus, so it's going to be 2 by 3 e power t less than 1. So e power t less than 3 by 2, that implies t less than log 3 by 2 base c. Okay, so this series converges for all t less than log 3 by 2. So expectation of e power tx exists for all t less than log 3 by 2. So in particular, we can pick our h to be log 3 by 2. So I can guarantee that this expectation e power tx exists for minus h to h, that is minus log 3 by 2 to log 3 by 2. So this expectation e power tx exists for all t from minus log 3 by 2 to log 3 by 2. We came up with a h which is log 3 by 2. Okay. So now, so hence mg of x exists, okay, as this expectation e power tx exists in some neighborhood of 0. Now let's compute MGF. MGF of x, mx of t, by definition expectation of e power tx, that is summation n equal to 1 to infinity e power tn tx of n. Again we end up with the same summation as above, which is 1 by 2 times summation n equal to 1 to infinity 2 by 3 e power t over to the power of n. Okay, so we should know one thing, this geometric series a plus ar square so on ar to the power of n, when it converges, we know it converges when mod r less than 1, the sum equal to a by 1 minus r, first term by 1 minus common ratio, but in this case a equal to r equal to both are 2 by 3 e power t, so this sum is going to be equal to 2 by 3 e power t, a by 1 minus 2 by 3 e power t, which is 1 minus r. Okay, a by 1 minus r. So 2 by 3 e power t by 1 minus 2 by 3 e power t. Okay, this whole thing gets simplified to e power t by 3 minus 2 e power t, which makes sense for any t less than log 3 by 2. So in particular, we can pick our interval to be minus h to h, where h equal to log 3 by 2. So this MGF exists in the interval minus h to h, where h equal to log 3 by 2, and MGF equal to e power t by 3 minus 2 e power t. Okay, so this is the MGF of the random variable, which is defined in the interval minus h to h, that is minus log 3 by 2 to log 3 by 2. Okay, MGF defined on this interval. Okay, fine. Next, here is an example of a continuous distribution with a PDF f of x equal to 1 by 2 times e power minus x by 2 for x positive, 0 for x less than or equal to 0. Let us see if MGF exists for this particular distribution. We have to see if expectation of e power tx exists for all t in some neighborhood of 0. Okay, so to see if this expectation exists, we need to consider this integral minus infinity to infinity mod e power tx f of x dx. If this integral converges for all t in some neighborhood of 0, then MGF exists, otherwise not. Okay, so here e power tx always positive, so we don't have to put modulus here, and here the support of x is interval 0 to infinity, so we simply integrate from 0 to infinity here e power tx, and the PDF is of e power minus x by 2 dx. So this we can write, if I write of outside, integral 0 to infinity e power t minus 1 by 2 x dx. Okay, this improper integral we can write of limit k tends to infinity integral 0 to k e power t minus 1 by 2 x dx. Integral of e power t minus 1 by 2 x dx going to be e power t minus 1 by 2 x by t minus 1 by 2. Here the limits are 0 to k. If I apply these limits, so when I plug in k, e power t minus 1 by 2 k by t minus 1 by 2. When I plug in 0, 1 by t minus 1 by 2. Okay, if I let k go to infinity, this term has nothing to do with the k, it will be as it is. Now the limit will be applied to only this one. Okay, now this integral will be convergent only when this limit exists. Here this limit e power t minus 1 by 2k, as k go to infinity, either will be 0 or infinite. It will be 0 when t minus 1 by 2 less than 0. It will be infinite when t minus 1 by 2 positive. Okay, so that means this limit exists only when t minus 1 by 2 less than 0, and that limit also going to be 0. In that case, it's going to be 1 by 2, 0 minus 1 by t minus 1 by 2. Okay, fine. So this integral converges only when t minus 1 by 2 less than 0. Therefore, this limit exists only when t minus 1 by 2 less than 0 and limit also equal to 0. Hence, expectation of e power tx exists for any t less than 1 by 2. Okay, fine. Now we can compute mgf mxt. By definition, expectation of e power tx. For that, we consider this one integral minus infinity to infinity e power tx f of x dx as support from 0 to infinity. Again, we end up with the same integral. So as limit is 0, so 1 by 2, 0 minus 1 by t minus 1 by 2. This gets simplified to 1 by 1 minus 2t. Okay, here to pick h, my choice of h is 1 by 2. As this mgf exists for all t belongs to minus infinity to 1 by 2. So in particular, we can pick small interval minus 1 by 2 to 1 by 2. Okay, that's why we can say that this 1 by 1 minus 2t makes sense in this interval minus 1 by 2 to 1 by 2. Okay, so hence mgf exists which equal to 1 by 1 minus 2t. Here the minus h2 h is this minus 1 by 2 to 1 by 2. Okay, so this is the mgf of the random variable. Okay, fine. Next, now let's look at examples of probability distributions for which mgf do not exist. Here is an example of a discrete random variable with support sx equal to 1, 2, 3, so on, and pmf px of n equal to 6 by pi square times 1 by n square for n equal to 1, 2, 3, so on. Okay, let us see if mgf exists for this distribution. Okay, let's see if expectation of e power tx exists for all t in some neighborhood of 0. Neighborhood of 0 means like for some h positive interval minus h to h. This is the neighborhood of 0. Okay. Now we need to consider this summation n equal to 1 to infinity mod e power tn px of n. If this series converges for all t in some neighborhood of 0, then mgf exists, otherwise not. Okay, so now here I don't have to write modulus for e power tn, so I write as it is e power tn, the px of n replaced by 6 by pi square 1 by n square. If I write 6 by pi square out, it's going to look like 6 by pi square, the series n equal to 1 to infinity e power tn by n square. Now let us see if this series converges for all t in some neighborhood of 0. In any neighborhood of 0, there will be some positive t, right? I am going to show that for any positive t, this series is going to be diverges. The reason is this. Okay, you should know some nth term test, that is, if a given series an, if you know that an is not going to 0, then you can say that this series diverges. Okay, because if this is convergent, an must go to 0. If an is not going to 0 means the series must be divergent. Here, for any t positive, e power tn by n square not going to 0. In fact, it's going to infinity because you can apply L'Hopital rule. Okay, so for any t positive, e power tn by n square not approaching 0, so this integral going to be diverges for any t positive. So we cannot pick any neighborhood of 0 in which this series converges for all t. That's why expectation of e power tx will not exist in any neighborhood of 0. So therefore, mgf doesn't exist. Okay, this is an example of a discrete random variable for which mgf do not exist. Next, let us look at example of a continuous random variable for which mgf do not exist. Okay, here's an example. Here is the continuous distribution, which is also called Cauchy distribution, with a PDF f of x equal to 1 by pi 1 by 1 plus x square for minus infinity less than x less than infinity. If the support of x is interval minus infinity to infinity. Let's see if expectation of e power tx exists for all t in some neighborhood of 0. Neighborhood of 0 means some interval around 0 like this, minus h to h for some h positive. Okay. To see if expectation of e power tx exists, we need to consider this integral minus infinity to infinity mod e power tx f of x dx. If this integral converges for all t in some neighborhood of 0, then we say MGF exists, otherwise not. Okay. Now here, we don't have to put modulus for e power tx as it is always positive. So it's going to be integral minus infinity to infinity e power tx, and the PDF is 1 by pi 1 by 1 plus x square dx. This we can write 1 by pi integral minus infinity to infinity e power tx by 1 plus x square dx. This integral we can break into two parts like this. 1 by pi integral minus infinity to 0 e power tx by 1 plus x square dx plus 1 by pi integral 0 to infinity e power tx by 1 plus x square dx. If this integral converges, then these two must converge. That means if one of these two diverges, then this must diverge. I am going to show that for any t positive, because every neighborhood must contain some positive t, for any t positive, this integral is going to be diverges. The reason is this. Analogous to nth term test for series, we have a integrand test for this improper integral. If this converges, that implies this integrand must go to 0 as x go to infinity. But that is not the case here. Here the e power tx by 1 plus x square for t positive must approaches 0 as x approaching infinity. This is the integrand test, but that is not the case. In fact, this integrand approaching infinity. You can verify that using L'Hopital rule. Okay, this integrand is not approaching 0 as x approaching infinity, so this improper integral cannot converge. So that means this diverges, so this diverges. So this integral will not converge for all t in any neighborhood of 0. Therefore, expectation e power tx will not exist in any neighborhood of 0. Hence, MGF of x doesn't exist. Okay, so fine. Let me clear this. So far, we have seen that CDF, PMF or PDF as an alternative specification for its probability distribution. Now we are going to state a theorem which says that when MGF exists, it also serves as an alternative specification for its probability distribution. Okay, here is the statement. The MGF of the random variable x uniquely determines its probability distribution Px, and conversely. If MGF exists, then it is unique. This theorem says that when MGF exists, it uniquely determines its probability distribution. Okay, fine. So, since MGF uniquely determines its probability distribution, it should not be surprising if we could obtain some properties of probability distribution directly from MGF. Especially for finding moments, MGF comes in very handy. Let us see how we compute moments through MGF. Okay? Here, if MGF exists in the neighborhood of 0, that is some interval minus h to h for some h positive, then derivatives of all order exist at t equal 0 and can be evaluated as follows. Okay, if you want to get the kth derivative of MGF with respect to t, that is kth derivative of expectation e power tx, you can actually perform this differentiation inside the expectation. The reason is this. For example, in the discrete case, expectation of e power tx is what? It is some summation x belongs to Sx e power tx p of x. Okay. If you want to differentiate with respect to t, the d by dt right hand side, when Sx is finite at least, we can actually do this term by term differentiation. Just because of generalization of u plus v rule, that is we can do d by dt e power tx px of x. Okay. Even Sx is countable infinite, still we can perform this term by term differentiation because of some nice convergence of this series in the interval minus h to h. Okay, so now it look like what? Expectation of this. Expectation of d by dt e power tx. In the same way, if x is a continuous random variable, in that case, expectation of e power tx means we write integral minus infinity to infinity e power tx f of x dx. If you want to differentiate with respect to t, so d by dt. Now, so due to Leibniz rule, we can actually perform this differentiation with respect to t under integral sign. We can actually do this because of Leibniz rule. D by dt e power tx f of x dx. Now this look like expectation of d by dt e power tx. Okay, even if you perform k times, you can just repeat this one. Okay, if you want to differentiate expectation e power tx k times with respect to t, you can actually do the differentiation inside expectation. That is, the kth derivative of expectation e power tx with respect to t going to be expectation of kth derivative of e power tx with respect to t. Okay, so now this derivative is going to be x to the power of k e power tx. Okay, now if you plug in t equal 0, the kth derivative of mgf at 0 going to be expectation of x to the power of k, because when you plug in t equal 0, you will have expectation x to the power of k e power 0, which is going to be expectation of x to the power of k, which is mu k dash. Okay, this is how MGF generate all the moments, hence the name moment generating function. Okay, fine. If MGF exists in the neighborhood of 0, that is in the interval minus h to h for some h positive, we just saw that derivatives of all order exist at t equal 0 for MGF. So we can express MGF uniquely using Maclaurin series expansion. Maclaurin series expansion is Taylor series expansion about 0 is called Maclaurin series expansion. Here is a Maclaurin series expansion for MGF. Okay, this is the Maclaurin series expansion for MGF. We know that the kth derivative of MGF at 0 actually kth non-central moment mu k dash, right? Okay, so we can see that coefficient of t to the power of k by k factorial in Maclaurin series expansion of MGF is what? Mu k dash. If you want to get all the moments, what you do is you expand given MGF using Maclaurin series expansion and read off the coefficient of t to the power of k by k factorial as mu k dash. So this is how you can get hold of all the moments of the distribution from MGF. Okay, fine. Note here, in this note, we are going to see how to compute mean and variance through MGF. Mean is what? First non-central moment, right? Mu1 dash. And we just know that the kth non-central moment mu k dash simply going to be kth derivative of MGF at 0. So, the first derivative of MGF at 0 simply going to be mean. This is how we can get hold of mean. Okay. Next, the variance. Sigma square is what? Mu2 dash minus mu1 dash whole square. That is expectation x square minus expectation x whole square, right? Okay. And from this mu2 dash we can write second derivative of mgf at 0, and mu1 dash is what? First derivative of mgf at 0. So this is how we can compute the variance. Sigma square is going to be second derivative of mgf at 0 minus first derivative of MGF at 0 whole square. Okay, so this is how we can compute mean and variance through MGF. Okay, just please keep in mind, in the next problem we are going to use these results to compute the mean and variance for given MGF. Okay, next. Okay, here's the problem. Here MGF is given. We have to find mean and variance of x. What is the MGF of x here? Mxt equal to p e power t by 1 minus of 1 minus p e power t, which is defined in this interval, minus h to h, where h equal to log 1 by 1 minus p. Fine. So from the above note, we know that mean mu equal to first derivative of mgf at 0, and the variance sigma square going to be second derivative of mgf at 0 minus first derivative of mgf at 0 whole square. Okay, this is how we get mean and variance through mgf. Okay, first, to find the mean, we need a derivative of mgf. Okay, first let us differentiate mgf with respect to t. Here mgf look like u by v form. Let's apply quotient rule, u by v rule, that is v u dash minus v dash u by v square. Okay, so the derivative of mgf with respect to t going to be, here u is p power t, v is 1 minus of 1 minus p power t. Here this is v and this is u dash. Derivative of p power t with respect to t again going to be p power t. So v u dash, this is v dash, this is u, by this is v square. V u dash minus v dash u by v square. Okay, this whole thing gets simplified to p power t by 1 minus of 1 minus p power t whole square. Feel free to verify this. Okay, now if we plug in t equal 0, so what we get here, p by 1 minus of 1 minus p whole square. Here 1 cancel, then you end up with a p by p square, that will be 1 by p. So the mean mu equal to 1 by p. Okay, now we got the mean. Now to find the variance, again we need a second derivative of mgf. To get the second derivative of mgf, let us differentiate once more with respect to t, the derivative of mgf, this one. Okay, again this look like u by v form. Again let's apply u by v rule. Here u is p e power t and v is 1 minus of 1 minus p e power t whole square. Okay, the second derivative of mgf with respect to t going to be this. Okay, this is v u dash minus this one v dash and u by v square. Okay, now if you plug in t equal 0, the expression look like this. The whole expression gets simplified to 2 minus p by p square. Feel free to verify this, it's easy, just things get cancelled and you will be left with 2 minus p by p square. This is the second derivative of mgf at 0. Okay, now we are in a position to find the variance sigma square. So sigma square going to be what? Second derivative of mgf at 0 minus first derivative of mgf at 0 square. So this is 2 minus p by p square minus 1 by p whole square. This is going to be 2 minus p minus 1 by p square, which is going to be 1 minus p by p square. Okay, so this is a variance. Okay, here mean mu equal to 1 by p and the variance sigma square equal to 1 minus p by p square. Fine. So this is how we compute mean and variance through MGF. Okay, let me clear this. Okay, here is the problem. Find all moments of x whose MGF is given. Here mxt equal to 1 by 1 minus 2t, which is defined in the interval minus h to h, where h equal to 1 by 2. Okay, fine. So what do we do? I told you that if you want to get hold of all moments, you try to write down Maclaurin series expansion for given MGF and you read off the coefficient of t to the power of k by k factorial as mu k dash. So we know that mu k dash is coefficient of t to the power of k factorial in Maclaurin series expansion of MGF, right? First we want to write down Maclaurin series expansion for given MGF. What is MGF here? So 1 by 1 minus 2t, 1 by 1 minus 2t we can expand like this. Summation k equal to 0 to infinity 2t all to the power of k. It actually follow from this. We know that expansion of 1 by 1 minus x is summation k equal 0 to infinity x to the power of k, which actually follow from extended binomial theorem. Here are some standard expansions follow from extended binomial theorem. But whenever we use extended binomial theorem, we are actually writing Maclaurin series expansion. What is extended binomial theorem? 1 plus x all to the power of u, which is a summation k equal to 0 to infinity u choose k x to the power of k. I told you that the proof of the extended binomial theorem follows from Maclaurin series expansion. If you write Maclaurin series expansion for the left hand side, that will be the right hand side. So whenever you are writing expansions that follow from extended binomial theorem, that means you are actually writing Maclaurin series expansion. Okay. So here you can see this one as Maclaurin series expansion for 1 by 1 minus 2t. Now that means here we got a 2 power k t to the power of k. Here, here we want to read of coefficient of t to the power of k by k factorial as a mu k dash. But I don't see k factorial here in the denominator. So we can adjust that by multiplying and dividing by k factorial like this. Okay. So now we can see that coefficient of t to the power of k by k factorial is 2 to the power of k factorial. Therefore, mu k dash equal to 2 to the power of k factorial for k equal to 0, 1, 2, so on. This is how we get hold of all moments from the given MGF. Okay, fine. Here is another problem. Find all moments of x whose MGF mxt equal to e power t square by 2, which is defined for all t from minus infinity to infinity. Here is the MGF mxt equal to e power t square by 2. First we want to write down Maclaurin series expansion for e power t square by 2. We know that e power x Maclaurin series expansion is summation k equal 0 to infinity x to the power of k by k factor. This is the Maclaurin series expansion for e power x. Now we should be able to write down Maclaurin series expansion for e power t square by 2 simply plugging t square by 2 in place of x. Okay, so it's going to look like this: summation k equal 0 to infinity t square by 2 whole to the power of k by k factorial because of this. Fine. Now this term gets simplified to t to the power of 2k by 2 to the power of k factorial. Fine. Okay. Now I see there are no odd powers of t. There are only even powers of t. So let's read off the first coefficient of t to the power of 2k by 2k factorial. But I don't see any 2k factorial in the denominator. We can adjust it by multiplying and dividing by 2k factorial like this. Okay. So we multiply and divide 2k factorial each term like this. Okay. Then coefficient of t to the power of 2k by 2k factorial going to be 2k factorial by 2 to the power of k factorial, which is going to be mu dash 2k. Okay. Therefore, the mu dash 2k is what? 2k factorial by 2 to the power of k factorial. Okay. And there are no odd powers of t. So coefficient of t to the power of 2k plus 1 by 2k plus 1 factorial we can take as 0. So the mu dash 2k plus 1 is going to be coefficient of t to the power of 2k plus 1 by 2k plus 1 factorial. So it's going to be 0. So all even order moments, the mu dash 2k is going to be what? 2k factorial by 2 to the power of k factorial. All odd order moments going to be 0 here. Okay, fine. Let me clear. Earlier I mentioned that these moments when exist, They give a lot of information about its probability distribution. In fact, knowledge of all these non-central moments can determine probability distribution uniquely. That is the next theorem statement. Okay. Here is the statement. Let mu k dash be the moment sequence of the random variable x. That is, we have mu1 dash, mu2 dash, mu3 dash, so on, mu k dash. So we have all non-central moments of all order. If the power series summation k equal to 0 to infinity mu k dash by k factorial t to the power of k converges absolutely for some t equal to t naught positive, then this moment sequence uniquely determines the probability distribution. Here we should know one thing. If this power series converges absolutely for some t equal to t naught, then this power series must converges absolutely for all t for which mod t less than t naught. That means this power series converges for all t in the interval minus t naught to t naught. If you take your choice of h to be t naught and this power series converges for all t in the interval minus h to h. Okay, and we also know that kth non-central moment mu k dash is actually the kth order derivative of mg of at 0. So we can actually write this power series in terms of mg of derivatives like this. The kth order derivative of mg of at 0 by k factorial, simply replacing mu k dash with this into t to the power of k, and this converges for all t in the interval minus h to h, okay, which is the neighborhood of 0. And we know that this is precisely Maclaurin series expansion for mgf. So you got moment generating function mgf. So this moment sequence is actually giving MGF, and we already know MGF uniquely determines the probability distribution. So that's why this moment sequence completely determines probability distribution uniquely. Okay, fine. Note, in this note, we're going to see the relationship between MGF of x plus b and MGF of x. Here is the relation. MGF of x plus b at t going to be e power tb times MGF of x at at. Okay, first of all, what is the MGF of x at t, which is the expectation of e power tx, right? Okay, now let us say y equal to ax plus b, where a and b are some real numbers. Okay, now MGF of y at t going to be by definition expectation of e power ty, right? So what is y here? Ax plus b. Okay, so this one we can write e power tb times e power tax. Okay, e power tb kind of a constant we can write down outside of the expectation. So e power tb expectation of e power at x, I can write like this. Now e power tb, see here this look like this, but in place of t we have a at, so we can write mx of at. Okay, so therefore mgf of ax plus b at t going to be what? E power tb times mx at. Okay, so this is the connection between mgf of ax plus b and mgf of x. Okay, fine. Let me clear this. Now we know that MGF uniquely determines its probability distribution when it exists. So technically, one should be able to find probability distribution, that is PDF or PMF, from its MGF. But this problem of finding probability distribution from its MGF is going to be easy in the case of discrete random variable, but not in the case of continuous random variable. First, we will see how to find PMF of the discrete random variable from its MGF. Okay. Now, finding PMF when MGF of discrete random variable is given. Let us say this is the given MGF defined in the neighborhood of 0 minus h to h for some h positive. First, we try and express given MGF in this form. Summation e power tx q of x, where x running over some countable subset of R and some function q of x over s. But we know MGF for the discrete random variable actually summation e power tx p of x, where x running over support of x. And you should know one fact that this family of functions of t always going to be linearly independent. That means one member here cannot be written as linear combination of other members. In that case, we must have a unique representation for this MGF. That means these two representations must be same. That means Sx must be equal to S and P of x must be equal to Q of x for all x belongs to Sx. Okay. Once we express given MGF in this form, immediately we can see the support and the PMF function. This is how we can find PMF of the discrete random variable from MGF. When it comes to the continuous case, we want PDF from MGF. In that case, we end up solving the following integral equation. That is, here M is known, MGF is given, F is unknown, PDF is not known. So, to get the PDF from this relation, you have to solve this integral equation. That is not going to be easy problem. We are not going to do in this course. Okay? Fine. Let me clear this. The problem here, MGF of the discrete random variable is given. We have to find the PMF of x. Here, given MGF already in the form that we want to see, this form. So, immediately we can read off the support and PMF values. Here, summation running over 1, 2, 3, 4. Okay. So, here Sx going to be 1, 2, 3, 4, and the PMF values at 1 is 1 by 10, at 2 is 2 by 10, at 3 is 3 by 10, at 4 is 4 by 10. Therefore, the support of x is set consisting of this 1, 2, 3, 4, and the PMF function is this P of x equal to x by 10 for x belongs to Sx. Okay? Fine. This is easy. Next problem. If the MGF of the discrete random variable mx of t equal to e power lambda of e power t minus 1, then find the PMF of x. This time, given MGF not in the form that you wanted to see, we wanted to see in this form e power tx q of x, where x running over some countable subset of R yes, then immediately we can say that this S is support and this Q of x is a PMF function. So our goal is to write given MGF in this form. Okay, fine. Let us start with a given MGF. So given MGF we can write like this: e power minus lambda times e power lambda e power t. This e power lambda e power t we can write in series form like this. Okay, because e power x is what? Summation k equal to 0 to infinity x to the power of k by k factorial. This is a Maclaurin series expansion for e power x. So here in place of x we are using lambda e power t. So we write e power lambda e power t got replaced by summation k equal to 0 to infinity lambda e power t whole power k by k factorial. Okay, fine. Now in the next, if I take e power minus lambda inside, e power minus lambda, lambda power k, e power kt by k factorial. Okay, if I group these things, I can rewrite like this. Summation k equal to 0 to infinity e power kt e power minus lambda power k by k factorial. Finally, now it is in the required form. Okay, so this look like summation k equal to 0 to infinity e power kt px of k. Now I can say that the support of x is going to be 0, 1, 2, 3, so on, and the PMF function px of k going to be e power minus lambda power k by k factorial for k belongs to Sx. Okay, so done. Okay, this is the PMF for given MGF. Fine. Next, here is the exercise. Here MGF is given, you have to find the PMF. Hint, use the binomial theorem to see in a required form. Okay. Suppose we have some partial information about probability distribution, like we know mean or mean and variance, stuff like that. Then can we say something about probabilities of certain types of events, like giving upper bound or lower bound for those probabilities? Answer is yes. Using some probability inequalities, we can actually give these upper bounds or lower bounds for probabilities of certain types of events without having knowledge of the actual probability distribution. Okay, now we are going to study some important probability inequalities. First, we are going to look at something called Markov's inequality theorem. Here is the statement: let u of x be the non-negative function of the random variable x. If expectation of u of x exists, then for every c positive, probability of u of x greater than or equal to c always less than or equal to expectation of u of x by c. This is the Markov's inequality. Okay, let's prove this. We are going to prove this theorem in the continuous case. Similarly, you can prove in the discrete case. Okay. Proof. Let us start with the expectation u of x, which is exists. So we can compute like this. Expectation u of x is integral minus infinity to infinity u of x f of x dx, where f is PDF of x. Okay. So here we are integrating from minus infinity to infinity. So this domain of integration we can break into two parts: x such that u of x greater than or equal to c, and x such that u of x less than c. So this integral we can break into two parts like this. Okay, here we are integrating over x such that u of x greater than or equal to c. Here we are integrating over x such that u of x less than c. The total union going to be all minus infinity to infinity. Fine. Now next we can write this inequality like this. The reason is, see, in this range of integration, u of x greater than or equal to c, so this integrand will be always bigger than or equal to this integrand. So this integral will be bigger than or equal to this integral. Okay. Now this is as it is. Okay. So that's why this sum is going to be bigger than or equal to this sum. Fine. Next. Next we can write this c out, and this integral going to be non-negative because u of x non-negative, PDF non-negative, integral of non-negative function again non-negative. So this will be non-negative. So if you want to get rid of this, so we can write like this. Still we can write this inequality. Grab c out. Okay. Still this is going to be greater than or equal to integral of f of x dx over x such that u of x greater than or equal to c. Okay, so since this is non-negative, fine. Now we are integrating PDF over this domain x such that u of x greater than or equal to c. That means this will give the probability of this event u of x greater than or equal to c. So this will be precisely probability of u of x greater than or equal to c. So therefore we can write like this. So the right hand side is going to be c times probability of u of x greater than or equal to c. Left hand side is what? Expectation of u of x. We have this. Since c positive, if you bring this side, so we can still have this inequality. The probability of u of x greater than or equal to c less than or equal to expectation of u of x by c. Okay. So this is the Markov's inequality. Fine. Okay. Let's look at some corollaries now. Corollary 1. Probability of mod x greater than or equal to c always less than or equal to expectation of mod x by c for any c positive. Simply follow from Markov inequality. Here our choice of e of x is mod x, non-negative function. Fine. Okay, here we are taking e of x equal to mod x. Then this statement follows from Markov inequality. Next, corollary 2. If x is a non-negative random variable, then probability of x bigger than or equal to c less than or equal to expectation of x by c for any c positive. X is non-negative random variable means which takes only non-negative values. Okay, so again this follow from Markov inequality. Here our choice of u of x is x itself. Okay, u of x equal to x, which is a non-negative function of x. So it follows from Markov inequality that probability of x greater than or equal to c less than or equal to expectation of u of x by c. Okay, fine. These are the two statements we can immediately see from Markov inequality. Okay. Next, theorem Chebyshev's inequality. Here is the statement: let x be a random variable with a mean mu and variance sigma square. Then for every k positive, probability of mod x minus mu greater than or equal to k sigma less than or equal to 1 by k square. So using Chebyshev's inequality, we can actually give upper bound for this type of event. Okay. Equivalently, we can also write this inequality. Probability of mod x minus mu less than k sigma always greater than or equal to 1 minus 1 by k square. Okay, this actually follows from this inequality because this event is complement of this event. Okay, so using Chebyshev's inequality, we can give lower bounds for this type of events. Okay, let's prove this. Again, we are going to use Markov's inequality here. Take u of x to be x minus mu whole square. Okay, here our choice of u of x is x minus mu whole square, which is non-negative function, and c is going to be k sigma. Here k positive and standard deviation sigma always positive, so this is going to be positive. This is our c, this is our u of x. Now we should know one thing: mod x minus mu greater than or equal to k sigma if and only if x minus mu whole square greater than or equal to k square sigma square, because k sigma positive, right? So this is true. So the probability of this event will be same as probability of this event. That is, probability of mod x minus mu greater than or equal to k sigma will be same as probability of x minus mu whole square greater than or equal to k square sigma square. Okay, this is our u of x, this is our c. Now here we can apply Markov's inequality. So probability of u of x greater than or equal to c is less than or equal to expectation of u of x by c, right? So therefore this probability will be less than or equal to expectation of u of x by c, right? So what is u of x here? X minus mu whole square. So expectation of x minus mu whole square by definition variance, right? So this is what? Variance sigma square by k square sigma square. So this one cancel. So we have this probability of mod x minus mu greater than or equal to k sigma less than or equal to 1 by k square. Okay, from this, if you write 1 minus probability of mod x minus mu less than k sigma will be less than or equal to 1 by k square. Okay, so if you bring this one this side, this one this side, you can actually write probability of mod x minus mu less than k sigma actually greater than or equal to 1 minus 1 by k square. Okay, so fine. So we also have this inequality. So using Chebyshev's inequality, we can give upper bound for this type of event. We can give lower bound for this type of events. Okay, not for all events. For certain types of events, we can give these upper bounds or lower bounds. Okay, fine. Okay, now let's do a problem. Before we proceed, in the Marcos inequality, probability of E of x greater than or equal to C less than or equal to expectation of E of x by C, where E of x is non-negative function of the random variable x and C is a positive. We don't have to worry about this equality included or not. We can also make this statement: probability of E of x strictly bigger than C will be less than or equal to expectation of E of x by C. We can also prove in the same way. Only thing is, when we break the integral into two parts, we break over the domain x such that E of x greater than C, and another part will be x such that E of x less than or equal to C. That's it. Okay, everything else will be same. So you'll end up with this result. So whether we include equality or not, still we can use this upper bound. Expectation of E of x by C will be upper bound for these both events. Whether E of x greater than or equal to C or E of x greater than C, for both we can use upper bound expectation of E of x by C. You don't have to worry about whether equality included or not. Okay. Fine. Example: suppose it is known that the number of items produced in a factory during a week is a random variable with a mean mu equal to 50. Question A: what can be said about the probability that a week's production will exceed 75? Question B: if the variance sigma square of the week's production equal to 25, then what can be said about the probability that week's production will be between 40 and 60? Okay, if x is a random variable which denotes the number of items produced during a week, then in question A, we want to say something about probability of x bigger than 75. In question B, we want to say something about x between 40 and 60. Okay, so here using Marcos inequality, we are going to give upper bound here. Using Chebyshev's inequality, we are going to give a lower bound here. Okay, fine. Solution: let x be the number of items that will be produced in a week, then x going to be the non-negative random variable. Using corollary 2 of the Marcos inequality, we can write probability of x bigger than 75 less than or equal to expectation x by 75. Okay, now expectation x here, the mean, which is 50, so 50 by 75 equal to 2 by 3. So the probability of week's production will exceed 75 will be always less than or equal to 2 by 3. Okay, so the question A answered using Marcos inequality. Okay, let me clear this. Next, question B: what can be said about the probability of week's production between 40 and 60? That is, probability of x between 40 and 60. Okay, so we're going to give a lower bound for this probability using Chebyshev's inequality. First, let us rewrite this event in appropriate form so that we can apply Chebyshev's inequality. Okay, so what I'm going to do, I'm going to subtract the mean mu equal to 50, right? Okay, so we subtract mean each side, so we have 40 minus 50 minus 10 less than x minus mu less than 60 minus 50, which is 10. Okay, so we have this probability of minus 10 less than x minus mu less than 10. So this we can write probability of mod x minus mu less than 10. Okay, where mu equal to 50. Now, so this we can write like this: probability of mod x minus mu less than 2 sigma. This 10 I can write 2 sigma. Sigma square, the variance is 25, right? That implies standard deviation sigma going to be 5. So this 10 can be realized as 2 sigma. So now this look like the probability of mod x minus mu k sigma, where k equal to. So using Chebyshev's inequality, we can write this probability greater than or equal to 1 minus 1 by k square, right? So k equal to, so 1 minus 1 by 2 square, this is going to be 3 by 4. So this is 0.75. We can say that week's production will be between 40 and 60 with the probability at least 0.75. Okay, so this is how we can use Chebyshev's inequality to give a upper bounds or lower bounds for certain types of events. Question is how tight these bonds can be. Let's try to see this through examples. Okay, here is the example of a probability distribution with a PDF f of x equal to 1 by 2 root 3 for minus root 3 less than x less than root 3, 0 otherwise. For this distribution, mean mu going to be 0 and variance sigma square going to be 1. Feel free to verify this. Now, if I take k equal to 3 by 2, okay, let's try to compute probability of mod x minus mu greater than or equal to k sigma using actual probability distribution. So this is our event mod x minus mu greater than or equal to k sigma. Here the mean is 0 and k we have taken 3 by 2 and sigma square is 1, right? That implies sigma is going to be 1. Okay, so this is 1. Okay, this is 3 by 2. Okay, so now that's why. So this is going to be what? Probability of mod x greater than or equal to 3 by 2. Let us try to compute the probability of this event using actual probability distribution. It's going to be 1 minus probability of mod x less than 3 by 2, which is 1 minus probability of minus 3 by 2 less than x less than 3 by 2. Okay, so to get this probability, we simply integrate the given PDF from minus 3 by 2 to 3 by 2. If you do that, you will end up with the answer 0.1339. So actual probability of this event is 0.1339. Okay, but if you try and apply Chebyshev's inequality, you try to say this is less than or equal to 1 by k square, which is 1 by 3 by 2 whole square. It's going to be 4 by 9. Okay, if you try and apply Chebyshev's inequality, the probability of mod x minus mu greater than or equal to k sigma will be less than or equal to 1 by k square, that is 1 by 3 by 2 whole square, that is 4 by 9, which is 0.44. Okay, here this upper bound is not so tight. Actual probability is much low, 0.1339, but you are trying to give a big upper bound. Okay, sometimes these bounds can be not so good. Okay, here is an example of a discrete distribution with a support minus 1, 0, 1 and the PMF values at minus 1, 1 by 8, at 0, 6 by 8, at 1, 1 by 8. Okay. Now let us compute mean and variance first. Here the mean mu going to be expectation x, which is going to be 0. And whenever mean is 0, variance is going to be same as expectation x square, because variance by definition expectation of x minus mu whole square, right? If mean is 0, which is going to be expectation x minus 0 whole square, that is expectation x square. So the variance sigma square in this case, expectation x square, which is going to be 1 by 4. So the standard deviation sigma will be 1 by 2. Okay, let's take k equal to here and let us compute the probability of this event using given PMF. Okay, now here the mean mu is 0, k we have taken 2 and sigma we got 1 by 2. Okay, it's going to be probability of mod x greater than or equal to 1. Okay, this 2 to cancel. Okay, now the probability of mod x greater than or equal to 1 means x can be either minus 1 or 1. So it's going to be probability of x equal to minus 1 plus probability of x equal to 1 is 1 by 8 plus 1 by 8, right? Okay, so 1 by 4. So probability of this event, actual probability of this event from the probability distribution is 1 by 4. But if you try and apply Chebyshev's inequality, you would say that this probability less than or equal to 1 by k square, still that is also going to be same 1 by 4. Okay, from Chebyshev's inequality, this probability will be less than or equal to 1 by k square. Here k equal to, right? So it's going to be 1 by 4. So here this bound is attained. Okay, the bound we are giving using Chebyshev's inequality actually equal to the actual probability. So sometimes these bounds can be very tight. Okay, next. Okay, now let us look at some other forms of Chebyshev's inequality. Okay, here is the one. Probability of mod x minus mu greater than or equal to epsilon always less than or equal to sigma square by epsilon square. What we know actually from Chebyshev's inequality, probability of mod x minus mu greater than or equal to k sigma always less than or equal to 1 by k square, where k is positive. Okay. So let's try to realize this inequality in that form so that we can apply Chebyshev's inequality to see this. Okay. Here this event mod x minus mu greater than or equal to epsilon, I'm realizing like this. Okay. I'm just multiplying, dividing by sigma here. Okay. Probability of mod x minus mu greater than or equal to k sigma form now. This is k sigma. Okay. So from this it must be less than or equal to 1 by k square. What is k here? Epsilon by sigma. Okay. So this will give you sigma square by epsilon square. So that's why the probability of mod x minus mu greater than or equal to epsilon always less than or equal to sigma square by epsilon square. Okay. So next we have this one. Probability of mod x minus mu less than epsilon will be always greater than or equal to 1 minus sigma square by epsilon square. Immediately follow from this because this event is complement of this event, right? So if you know this, you should know this. Fine. So these are other forms of Chebyshev's inequality. Fine. Next, we are going to see another important inequality, something called Jensen's inequality. Before we see that, we need to understand what is called convex function. Here is the definition. A function phi defined on interval a b is said to be convex if phi of tx plus 1 minus ty less than or equal to t phi of x plus 1 minus t phi of phi for all xy in the interval a b 0 less than t less than 1. This is the definition. Let me explain through examples. Okay. Here I have taken two examples. One is convex, other is not convex. Okay. Let me explain why the first one is convex function. Let's say here x and y between a and b, 0 less than t less than 1. Then tx plus 1 minus ty sitting somewhere between x and y. Let us say this is the location of tx plus 1 minus ty. On the graph, its image is going to be this. Okay, this is the phi of tx plus 1 minus ty. Okay, but t phi of x plus 1 minus t phi of phi is this. Okay, it's going to be this. Here is the location for t phi of x plus 1 minus t phi of phi. As you see here, in this case, this inequality holds. We can check for any t between 0 and 1, same thing will happen. So this is an example of a convex function according to definition. Okay, let me explain why the second one is not convex. Okay, let's say between a and b. Okay, for 0 less than t less than 1. Let's say this is a tx plus 1 minus ty. On the graph, its image is going to be this one, phi of tx plus 1 minus t phi of phi, but t phi of x plus 1 minus t phi of phi location will be here. Okay, t phi of x plus 1 minus t phi of phi. As you see, this time this inequality doesn't hold, so this is not a convex function. Okay, there is another thing called concave function. For that definition will be here we put inequality this side. Okay, this is not even going to be concave function because we can come up with another choice of t for which that inequality also fails. Okay, so this is neither convex function nor concave function. Anyway, we are focusing on convexity here. One thing you can observe in the case of convex function, at any x comma phi of x, if you draw the tangent like this, okay, if you keep drawing tangent as the increasing function of x, you see the slopes are increasing. Okay, so for a convex function, these slopes are increasing functions of x. Okay, so If phi is differentiable, we know that phi dash x actually denote the slope of the tangent at x comma phi of x, right? So this must be increasing function of x. That is, phi dash x must be less than or equal to phi dash y for x less than y. Okay? If phi is twice differentiable, then derivative of the phi dash x must be non-negative because phi dash x must be increasing, right? So that means double derivative must be non-negative function. Okay, so for a differentiable function, we can verify whether function is convex or not just looking at the whether phi dash x is increasing function or not. Okay, if it is twice differentiable, simply look at the second derivative. It must be non-negative if phi dash x is increasing function. Okay, so most of the time we will be dealing with a differentiable function. So we don't have to look at the definition to verify whether a function is convex or not. If it is twice differentiable, simply look at double derivative. If it is non-negative, yes, otherwise no. Okay, so that's the thing. Okay, in the next theorem, I'm going to state these facts. Theorem: if phi is differentiable, phi is convex if and only if phi dash x less than or equal to phi dash y for x less than y. Okay, if phi is twice differentiable, phi is convex if and only if phi double dash x non-negative for all x in AB. Okay, this is how we check whether a function phi is convex or not. Okay, fine. Now, Jensen's inequality. Here is a statement: if phi is a convex function on open interval I and x is a random variable whose support is contained in I and has a finite expectation, then phi of expectation x less than or equal to expectation of phi of x. This is the Jensen's inequality. Okay, we are going to prove this theorem in special case assuming phi is twice differentiable, so that it's going to be easy. Of course, in general this statement is true, but we will prove in special case. Okay, so we prove this inequality assuming phi is twice differentiable on I. Okay, first of all, we need to realize that this mu expectation of x will be inside I. For example, if you think I is the interval AB, okay, as Sx is contained in I, so random variable will be between A and B. Then if you take expectation each side, so expectation x also between A and B. That's why the mean mu will be again sitting in I. Okay, the mu belongs to I. Okay, fine. Now we are going to write down Taylor polynomial of second degree about mu for phi. Okay, so this is the Taylor polynomial of second degree for phi about mu like this. Phi of x we can write phi of mu plus phi dash mu x minus mu by 1 factorial plus phi double dash c x minus mu whole square by 2 factorial, where c lies between mu and x. This is actually generalization of Cauchy mean value theorem. Okay, fine. Now if we write this expression in terms of the random variable x, we get this phi of x equal to phi of mu plus phi dash mu x minus mu by 1 factorial plus phi double dash c x minus mu whole square by 2 factorial. Here phi is convex, so we know that phi double dash c going to be non-negative and x minus mu whole square always non-negative. So this whole term will be non-negative. If you want to get rid of this, so you have to put inequality this side. Okay, now let us take expectation each side, then we will have expectation of phi of x greater than or equal to expectation of phi of mu plus phi dash mu x minus mu. Okay, the reason is this: if g1x greater than or equal to g2x, you should know that expectation of g1x greater than or equal to expectation of g2x. You can easily see from the definition of expectation, this is true. That's why we should have a same inequality like this. Now, if I apply expectation inside, phi of mu constant, phi dash mu constant, so So expectation will be applied to only this x minus mu. So phi of mu plus phi dash mu, expectation of x minus mu, which is the first central moment, is going to be expectation x minus mu. So mu minus mu, this is 0. So we have expectation of phi of x greater than or equal to phi of mu, and mu is what? Expectation x, right? So we can write expectation of phi of x greater than or equal to phi of expectation x. So we can also write like phi of expectation x less than or equal to expectation of phi of x. Okay, so this is the Jensen's inequality. Fine. Next we will see one application. We already know this expectation x square greater than or equal to expectation x whole square. We have seen earlier, but this one immediately follow from Jensen's inequality, because if you take phi of x equal to x square, the phi double dash x is 2, which is a positive. That means this phi is convex function. Now if you apply Jensen's inequality, we have expectation of phi of x greater than or equal to phi of expectation x. That is expectation x square greater than or equal to expectation x whole square. This follow from Jensen's inequality. So, okay, fine. Next problem. In this problem, we are going to prove a famous inequality, that is harmonic mean less than or equal to geometric mean, which is less than or equal to arithmetic mean. Okay. We are going to prove this inequality using Jensen's inequality. Okay, fine. First, let a1, a2, an be n positive numbers. Then this is the arithmetic mean, am equal to 1 by n summation I equal to 1 to n ai. And this is the geometric mean, gm equal to product I equal to 1 to n ai equal to the power of 1 by n. This is a harmonic mean, hm equal to n by summation I equal to 1 to n 1 by ai. Okay, fine. Now first of all, let us take the random variable x with the following distribution. Let x be the random variable with the support sx equal to a1, a2, so on an, with the pmf px of ai equal to 1 by n for I equal to 1 to n. Okay, this is the random variable with this distribution. Now expectation of x going to be what? Summation I equal to 1 to n px of ai, and this equal to 1 by n, right? So it's going to be 1 by n summation I equal to 1 to n ai. This is nothing but arithmetic mean. So expectation of x is 1 by n summation I equal to 1 to n ai. Okay, fine. Next, let us see what is the expectation of log x. Now expectation of log x equal to summation I equal to 1 to n log ai px of ai, and this pmf values are 1 by n for all I. So it's going to be 1 by n summation I equal to 1 to n log ai. This we can write log of a1, a2, so on an. So that's why we can write this equal to log of product I equal to 1 to n power 1 by n. Okay, you should know something about logarithms here. So this is nothing but log of geometric mean. Okay, expectation of log x nothing but log of geometric mean. Fine. Next, now let us consider the convex function phi of x equal to minus log x. Why this is going to be convex? If you look at the double derivative, it's going to be 1 by x square, which is positive. So therefore phi is convex. Okay, minus log x is convex function. Now let us apply Jensen's inequality for this convex function minus log x. So we have, by Jensen's inequality, we have expectation of phi of x greater than or equal to phi of expectation x. Now let us apply for our convex function minus log x. So we have expectation of minus log x greater than or equal to minus log of expectation x, and expectation of minus log x we can write minus expectation of log x. If you cancel out the minus, then inequality will be reversed. You will end up with this. You have expectation of log x less than or equal to log of expectation x. We already got expectation of log x as logarithm of product I equal to 1 to n ai or to the power of 1 by n. Okay, and we got expectation of x is 1 by n summation I equal to 1 to n ai, right? So log expectation of x going to be what? Logarithm of 1 by n summation I equal to 1 to n a. Okay, so now we have this. So logarithm of product I equal to 1 to n ai whole to the power of 1 by n is less than or equal to log of 1 by n summation I equal to 1 to n ai, and log is increasing function, so we must have this one. Okay, so we should have product I equal to 1 to n ai whole to the power of n less than or equal to 1 by n summation I equal to 1 to n ai, because log x is increasing function. So this is exactly geometric mean, this is exactly arithmetic mean. So we have GM less than or equal to A. Okay, fine. Next we have to show harmonic mean less than or equal to geometric mean. So instead of doing everything from scratch, now we are going to show HM less than or equal to GM actually from GM less than or equal to A. Okay, so this is how we are going to do. Okay, we are going to apply AM-GM inequality for these numbers B1, B2, Bn, where Bi equal to 1 by Ai. Okay, so we apply AM-GM inequality for this B1, B2, Bn. So what is the AM-GM inequality we got? GM less than or equal to AM, right? Okay, so we should have product I equal to 1 to n, Bi all to the power of 1 by n less than or equal to 1 by n summation I equal to 1 to n Bi. This is the GM less than or equal to AM. Okay, fine. Now let's replace Bi with 1 by Ai. Then we have this. Okay, product I equal to 1 to n 1 by Ai all to the power of 1 by n less than or equal to 1 by n summation I equal to 1 to n 1 by Ai. Now this one we can write reciprocal of this one 1 by product I equal to 1 to n ai all to the power of 1 by n. The right hand side as it is less than or equal to this. Now if I bring this one this side, this thing this side, so we end up with this. So we have n by summation I equal to 1 to n 1 by ai less than or equal to product I equal to 1 to n ai all to the power of 1 by n. This is exactly HM, which is less than or equal to this is GM. So we have HM less than or equal to GM. So we have from 1 and 2, we finally have harmonic mean less than or equal to geometric mean, which is less than or equal to arithmetic mean. Okay, this is the proof using Jensen's inequality. Fine. So let me stop now. Thank you.